Welcome everyone to today's Monash Software Systems and Cybersecurity seminars. Today we are very happy to welcome Dr. Chengjun Cai, who is currently a research fellow in City University of Hong Kong. He got his PhD degree in computer science from City University of Hong Kong in June 2021. Before his PhD candidature, he worked as a research assistant at the same university from 2016 to 2017 and got his bachelor's degree in computer science and technology from Jinan University in July 2016. He has published more than 16 papers in peer-reviewed international conferences and journals like ACM-CCS, IEEE Infocom, ICD-CS, and TDSC. And he received a Best Paper Award in IDSC in 2019. And his research interests include decentralized data-driven applications, blockchain security, and applied cryptography. And today, Dr. Cai will talk to us about Vizard, a metadata-hiding data analytics system with end-to-end policy controls. Thank you, Chengjun. I'll leave the scene to you.
Yeah. Okay. Can you see my slides?
Yep. Yeah. All good.
Yeah,
and for the attendee, if you have any questions, you can use the Q&A button to ask your question, and I'll monitor it and ask to Chengjun.
Yeah. Feel free to just interrupt me and ask your question. So first, thank you for the introduction, and I'm very happy to be here to show you one of my work that is done in last year and published in ACM-CCS 2022. And I'm Chengjun Cai, and I want to have a quick introduction about my institute. So some of you may very familiar with CTU of Hong Kong, and actually my institute is in mainland China, so it's actually a new campus that is set by CTU in the Greater Bay Areas. So and now if you are interested in my institute, I want to share with you some good news is that the deanship and also the headship positions are also open for recruitment. And if you all just want to be professors and associate professors or APs, you can also apply for the job, and you can see this link and just find more information for that. Yeah. So also a little introduction for me. I'm currently a research fellow, and I'm soon will be an AP in CTU Dongguan. And as mentioned by Mohammed, I'm focused on privacy preserving technologies and also blockchain and AI security. And I currently have 2 PhDs. Yeah. So I will soon post more PhD positions or RA positions. Please stay tuned. So if you're interested, and join my group. Yeah. So we start. So as we all know, there are more and more data being generated in our daily lives. But just instead of just collecting them as raw data, gathering the data together and then do aggregation to extract useful knowledge from them is a more practical approach. But among the just many data analytics applications, many of them, like healthcare monitoring, we need to access our sensitive data. Therefore, to protect user-sensitive data from being leaked to others, a long line of work has explored how to protect the data by encryption. But while the confidentiality of the data can be protected, the loosely controlled attacker can still deviate from the privacy policies that are defined by the owners and misuse their data in unauthorized tasks. And currently, other than relying on a notice and consent setting, there's no assurance in existing works for privacy compliance. Actually, this problem for privacy compliance was first formalized by SEC which was published 1 year ago in OSTI. In general, that fulfills the requirements for both data confidentiality and privacy compliance with the following two steps. In the first step, ZEP enables owners to define their own policy that controls how their data can be shared and processed. For example, in a heart rate monitoring application, an owner can define a policy that controls which hospitals can use his data and for what purpose. And when later some query issues an analytic task, and ZEP executes the task by first finding the match owner's data, and then conduct the analytic task over those policy match data to generate the result. And lastly, the above two steps will be verified for enforcement. And the querier will obtain the result only when the underlying process is proven correct. In that, such a verification process is guaranteed by a separated layer of federated committee. And here we omitted design details of that due to time limits. But while ZEP can further enhance owner privacy control, we observe that the added policy can enlarge the attack service and help attacker to infer owners' sensitive data. Consider that an owner decides to authorize his data to an analytic task, and later the attacker search about the task on Google or social media and find out that it was initialized by an oncologist. Even though the owner's data is encrypted, the attacker can still learn that the owner might suffer from cancer from the site information revealed by the data policy, which will surely violate our privacy protection goal for data owners. To solve such a problem, a first attempt is to encrypt the policy and later leverage secure computation techniques to decrypt and use the policy in a secure manner. However, this approach can only preserve the confidentiality of the underlying computation process. A curious server can still determine whether an owner's data has been used for a given task by also observing other metadata like data access patterns and infer the same amount of sensitive information about the owner as before. Therefore, in order to achieve end-to-end private analytics, we observe that apart from protecting the data and enforcing privacy compliance, we should also carefully protect the policy and the data access pattern during the analytic process. Here is an example of a noise monitoring application. The data owner submits his data and access pattern policy to our system, indicating that maybe his data can only be used by the querier with a specific ID. For example, scientists with very unique identification. As stated before, the access policy should be hidden in our system. Now, for example, a querier with exactly the same ID that is specified by the owner did submit a query to our system. We will later use this ID as input to privately select the match user's data and do the aggregation with access pattern protection in mind. So we can see that here actually every querier's ID will be put through our system, and only the match owner's data will be used. So in this way, we can do the metadata-hiding analytics with owners can define their own access policies. So in Vizard, we have not considered the protection for query predicates to ease our construction complexity. And we think it will be very interesting to further add such protection for private and achieve a more full-fledged protection. And to achieve our goals, a traditional way is to combine secure computation techniques with oblivious RAM or ORAM to hide which data has been accessed during the secure computation process. However, most ORAM construction exists today would generally incur heavy computation costs, and which makes them very difficult to adopt in real deployments. So in Vizard, our idea is to follow a latest trend and use a distributed point function to achieve metadata-hiding analytics. And so that we can provide effective protections to the data, the policy, and the data access pattern at the same time without sacrificing the computation efficiency. So I will first introduce a little more about the DPF, if you do not are very familiar with this primitive. So for a point function f that only evaluates to beta at point alpha and equals 0 at any other points, DPF is constructed by secret sharing the point function f into two function shares, such that the summation of their evaluation outputs is the corresponding output value of the point function f. I will not touch too much of the detail here, and if you want to see the theoretical analysis of the security proof, you can refer to the seminal paper that is published in CSS 2016, and also I think there are some more variants of the this such construction published in recent years. In general, DPF assumes two non-encoding servers, and each of the generated function share will be given to one of the two servers. DPF guarantees that any attacker that compromises only one of the two servers can learn nothing about the secure index alpha or its beta embedded in the DPF key strings. In recent years, DPF has been used in many secure applications like oblivious messaging systems, private information retrieval, also machine learning, and many other interesting fields. And next, we will show how to use DPF to construct our Vizard system. And so consider now a owner I participate in a healthcare analytic task that requires him to submit heart rate data in a fixed frequency. For some security reasons, like reputation level requirements, owner I may only want his data to be processed by scientists in a specific company. For example, just scientists in MIT or scientists in Monash. Yeah. Using these two data as input for DPF, owner I generates two DPF key shares, and each server will store one share respectively. Now to conduct summation queries over matched owner's data, the querier will need to submit also its corresponding information to the servers. For example, a proof that indicates he's actually a Monash scientist. The server will then use that information as evaluation input and just go through all the owner's DPF key shares and calculate the sum of those evaluation results. It's interesting to see that we can directly obtain our design result by adding those two sum results generated by the two servers, as only match owner's data value will be used, and other unmatched owner's evaluation result will equal 0. For security, it's apparent that since each server will go through all owners' DPF keys, they cannot learn which owners' data are matched and used in the summation process. Based on this simple yet efficient construction, we have further explored the following 3 challenging problems that can make Vizard more efficient and practical. First, since the basic solution requires the owner to generate a pair of DPF keys for each data value, it may incur linear key generation costs if we want to support time series data, which can make our system impractical for research-constrained devices like wearable devices. Besides, for enhancing the functionality, Vizard should also support rich policy configurations with AND or and NOT operators, and provide enriched result release control to ensure a truly end-to-end policy control environment. Due to the time limit, I will just briefly show the solution ideas to each of these challenging problems apart. First, for the time series analytics, each data owner will periodically submit their data value to Vizard for analytics. Here, our observation is that while the data stream values change over time, the data policy defined by each data owner could remain unchanged for a very long period. That is, the policy string alpha inputted for DPF key generation will remain the same. Based on this important observation, our key idea is to decouple the data values from the DPF keys. Now, the DPF keys will only embed a control value 1 inside, and we need not to update DPF keys as long as the policy remains unchanged. Now, for streaming data analytics, Query may issue a time window based task that wants to aggregate data values, for example, submit between apples T2 and T4. As now the data value is stored directly on each server, they can first calculate the aggregated stream value for that query time window. Then each server will, as the same, go through all the owners to do the DPF key evaluation as before. But differently in this new process, since the data value is not embedded in the DPF keys, they need to additionally embed the value by multiplying it with the DPF evaluation result. And now, assume the both servers obtain the same database. The sum of the 2 servers' outputs is thus the analytic results we desire for data values submit between the apples T2 and T4. Following this efficient workflow, the remaining challenge is how to encrypt owners' data values for privacy protections. And in Vizard, we have designed a customized construction based on a seminal work program, and we have further utilized a stream efficient scheme for boosting the time window-based aggregation process in step 1. And second,
Chengjun, can I ask a question?
Yeah, sure.
So what is this homomorphic encryption scheme that you use? Is it called TimeCrypt or something?
Yeah, TimeCrypt is one server version homomorphic encryption for streaming data. And actually, because we have 2 servers in our Vizard system, so we change it to a 2-server version. But the underlying process is remains the same as the TimeCrypt. Yeah.
Mm-hmm. So TimeCrypt is the name of the homomorphic encryption, is that right?
Yeah.
Okay.
But it's just for a single server. We have transferred it, extended it to a 2-server version and fits our system.
Mm-hmm. Okay. Thanks.
Okay, any other question? We use that homomorphic encryption because we need to make sure that the two server have the same encrypted database. Yeah, so that we can later use our workflow to get the design result. Yeah, so we use that homomorphic encryption. First, we need to make sure that the use program to let the two servers to get the same ciphertext, and then we think how to encrypt that ciphertext, and because we are dealing with streaming data, so we actually use that time crypt to as the concrete encryption scheme. So I will continue. So, and second, for the SQL database, we envision that this is actually an observation that we think owners might also want to set enriched and more complex data policies to better regulate data usage rights. So in Vizard, our goal is to achieve that such enriched functionalities without adding burdening cost to our system. So how to do that? First, for supporting the AND and NOT operators for the data control policies is much easier, as we only need to concatenate the policy conditions to achieve AND operators. And for NOT operator, we can also carefully inverse the DPF output value to provide an opposite result. That's actually very easy. But for the OR operator, and naive idea may be to just generate a pair of DPF keys for each condition, and later evaluate all the keys during the analytic process. But obviously, this will incur linear evaluation costs when the number of conditions scales. So in Vizard, we instead follow a recent work and use Kaku hash for indexing all the conditions DPF keys, so that we can later only evaluate a constant number. In our case, is 3 DPF keys, even though the number of conditions scale. But we observe that actually it comes at a cost of query accuracy, or so there's a parameter of the Kaku hash that we can choose to make that failure probability very low. So here's a true application example we support in Vizard. We actually we have just provided 5 general conditions descriptions for the user to fill in, and later the user needs also to describe their relation so that we can know which operator we need to care about. As different operator, as we mentioned before, different operator requires different processes. Then those conditions will be hidden as DPF keys for protection. And later, we can, when a query came, we can extract appropriate inputs from the consumer's queries. For example, C2, C3, and C5 for our example, to securely do the metadata-hiding analytics. So this is one of the concrete example we provide. So lastly, we also want to share some of the ideas for Vizard release control. In Vizard, we also follow a recent trend and design a decentralized committee for securely enforce the Vizard release policies. And the trustees in the committee will be randomly selected by a secure protocol for achieving Byzantine security. So we have now also identified two other release policies. So one is to we want to ensure that there is enough privacy protection for the result before it is released to the public. And this is actually achieved by asking the committee to jointly and securely generate a decentralized version of DP, so that we can ensure that a perfect amount of DP noise will be added to the result before release. And for the secure trading, it's actually based on one of my work that we use the distributed key generation, and we use that process to make that the diffusion key of the knowledge or the result is securely managed by the committee, so that only when when the consumer has paid on the blockchain, so all the committee members can check whether he has paid on the blockchain. So and the consumer will get enough amount of diffusion shares from the committee members, and then recover the result. So and the committee is to it can enforce that because the blockchain is transparent and everyone will just follow the payment record on the blockchain to make their own decision. So that is just three example release policy we support in Vizard. And I think it will be also very interesting to explore other useful control policies to just provide other more meaningful owner protections. So and I forgot to mention those release policies actually also jointly designed by the owners so that they can just make up the perfect appropriate amount of DP noise or the payment amount for their result. Yeah. So lastly, for the evaluation, I want to just quickly go through the experiment configurations. So we test the performance of Vizard in a practical 2 server setting, where the 2 servers are situated in 2 different regions in the Amazon cloud. So also, we have successfully built Vizard on top of an existing and widely deployed data streaming platform named Apache Kafka, so that we can enjoy more effective streaming processing speed, both in the data submission and intermediate data exchange phases. For the evaluation result, first, the processing cost, we can see that the execution overhead for both the data owners and the 2 servers are efficient, and which makes us our system very deployable for various IoT settings where the operation devices have only constrained resources. And for the query cost, we have used plain text processing where both the data and policy are not protected, and also compare with Z, where only the data is protected as a baseline for comparison. And in the figure, we can see that by Vizard only incurs a very low overhead compared to Z. And we think it's a very acceptable trade-off for much stronger privacy protection, because we think that actually is policy can leak very much metadata that will be do great harm to the owner's privacy. And so this is much very quick introduction of what we have done in Vizard, and metadata hiding data analytic system with owner-centric control for data usage rights and release control for more advanced protection. So end-to-end control here first is to let the owners to control how the data will be used, and also let them to control how their result can be released. So that's we think is very complete control flow for goes all around to the data and the result, and that's end-to-end. And we hope this new system can help break the troublesome data silos problem today and facilitate large-scale data stream analytics service. And our code is available on GitHub, and if you are interested, you can try out our prototype. And as a path ahead, actually, one of my students actually working towards how to extend Vizard to support machine learning. Actually, it's a very similar question because the data or the model updates, the participation history of which machine learning task we are participating in is also leaking very much metadata that can harm our privacy. For example, if you are participating in a cancer study, machine learning task, or or a specific task in a region, in a specific region, so that participating history, like we introduced in Vizard, can also be very privacy leaking. So and one of our current design structure is to integrate Vizard with federated learning, because we all learn that federated learning also need to do a model update aggregation so that we can generate a new global model and distribute that global model to all the participants. So so that we want to extend Vizard to this federated learning so that no one can learn which training task the users has participated. Yet we in the process we want to achieve this goal. We have confronted many challenges, such as the many models have a different model structures. So if you submit different model updates, different sizes of model updates, it's actually leaking some of the volume thing. So it has a potential leakage. And also, because those participants are hidden and no one knows which they are participating in, so it may pose more threat because those participants may do more malicious behaviors. For example, it may make those poisoning attacks or other attacks more easy to launch, because the identity of the participants now are hidden. But we also test some of the poisoning defense and apply them to federated learning. We find out that actually they are very expensive to use, because we need to also protect the data privacy in mind. So how to protect data privacy and also doing the data poisoning attack defenses, and without incurring much computation costs, it's actually a very challenging problem, and we are now working towards that. And so this is actually what I want to share with you today. So if you have any question, I'm very happy to answer.
Thank you very much, Chengjun, for your very interesting talk. I'll first ask if anyone has any questions. And maybe while everyone thinks about their questions, I might start with my own question. If you have a question, you can either type in the Q&A chat. Okay, maybe there's actually one question. I'll start with the audience question. So there are multiple questions from Shantanu. Hi, very nice work. Thanks for the great talk. Please let me know, do you store data in clear text or encrypted?
Yeah, all the stored data are always in protection, so they are encrypted.
Yeah, and then the follow-up question is, if encrypted, which encryption technique you used?
As I answered your question before, is using a streaming homomorphic encryption proposed by TimeCrypt. We extended to a two-server version.
And then the follow-up to that is, can the technique check policy containing both and or clauses without revealing access patterns?
Yeah, this is a very interesting question. Actually, we do not use very combination of those and or and not operators, because actually it poses very much changes. And we think one of the recent work named Waddle, actually they support various types of combinations of and or and not operators. But in their paper, they actually use free servers to reduce the cost. And we think by adding an additional server in Vizard, we can also achieve the very complex combinations of those operators, and without incurring very expensive costs.
Okay. And the last part of the question is, do you focus on volume leakage also?
No, we have not focused on that. Actually, we request the owners to periodically to submit their data to our system, so that we do not have that timing based attacks. So and it's also very interesting to show how to learn how to prevent avoid the periodically and submission requirement for the owners, and still achieve the same time of protection. Thank you.
Yeah, Shantanu says thank you as well. And there is another question. Can you please tell what was the role of Kafka here?
Yeah, the Kafka here is actually because we are dealing with data streaming. So Vizard can be worked without Kafka, but it may we need to handle a lot of the streaming processing stuff. So the use of Kafka here is just really a streaming optimization to help us to boost the processing speed. And the second one is because we observed that actually Kafka has been used widely in the streaming applications. So we want to test whether our work Vizard can be integrated with Kafka, so that we can actually help to do a more secure version of Kafka. So we integrate Kafka here in our experiment for testing its practicality.
Okay. Yeah. Thank you. So we have time for a question if anyone has any more questions, and you can think about your questions while I ask mine. So you had this slide about this release enforcement. I think you wanted to use some kind of like blockchain setting. Yeah, this one. So I couldn't quite understand how blockchain fits into the overall picture. Like you had the two server setting, and then like where does the blockchain fit in here?
Actually, blockchain is just for the money payment. If you do not need the money payment, or your payment is not blockchain related, you can actually use a centralized other monetary systems, so that yeah. But our goal here is we want to achieve this money secure swap of the money and result in a decentralized way. So so we think blockchain handling money may be a very good fit. So because it's transparent, and we can use that decentralized community as an enforcement to each of the trustee in the committee, they independently check whether blockchain the consumer has paid, and then he give out his share. So because only blockchain can provide such transparency, so we can guarantee that actually the payment has been made and fairly made as before the result is released to the consumer. Yeah, that's why we want to use blockchain. You do not want that decentralized property. You can always use other centralized allow a trusted party here and do the fair swapping. Yeah, that's okay. But want to avoid such centralized party. Yeah.
Yeah, I see. Yeah, thank you. And any last questions from anyone?
Yeah, if you have any question, I think you can always send emails to me, and I'm very happy to answer your question.
Yeah, thank you very much, Chengjun, for your very interesting talk, and thank you everyone for tuning in. Hope to see you all in the next seminar. Thanks.
Yeah, thank you for the arrangement, and thank you for participating. Yeah, thank you.